Hello everyone! In this video, we're going to be playing around with simulating some snowflakes. It's easy to think that something as complex as the geometry of a snowflake must arise from extremely complex laws of nature. But a couple weeks ago, I actually came across this paper on simulating snowflakes via a rather simple 2D cellular automata. A cellular automata is a type of simulation, usually run on a grid, where each grid cell acts like a little computer, or an automaton, which can look at the state of the cells nearby and obey some rules that we set for it. By far, the most famous cellular automata is Conway's Game of Life. Here, every cell is either black or white, corresponding to dead and alive respectively, and they follow the rules that any live cell with less than 2 or more than 3 live neighbors dies, and any dead cell with exactly 3 live neighbors comes to life. By just applying these simple rules to our grid here, we can see some extremely complex behavior emerging which almost resembles microscopic life forms. This behavior is in fact so complex and capable that with the right initial conditions, you can even simulate the game of life within itself. Back to our simulation, I'm working on this in Blender, and if you've ever used the software before, you'd be fair to assume that we'll be working with a geometry node simulation. I actually want to build our simulation in the compositor though, with image textures, so that we can leverage at least some GPU acceleration. Running simulations in the compositor is actually pretty straightforward, though as far as I'm aware, no one else has figured out this trick before. See, in the compositor, we can render out a brief image sequence using a file output node, making sure to write them out as zip EXRs. Then we can just bring that sequence into the compositor and offset the frames by -1. Now this image node is always grabbing the most recently rendered frame, and our image and file output nodes will act like the in and out ends of a recursive loop. We can then set some initial input by checking if we're on the first frame or not, and now we have a fully functional simulation zone with access to all the functions of Blender's compositor. This is by no means the best or most efficient way to run really any simulation. That would of course be to program it with something like OpenCL, but it's perfectly capable and it'll let us work within the node interface in Blender that I'm used to. With that out of the way, we can start out by immediately running into a problem. See, the simulation we want to run runs on a hexagonal grid rather than the Cartesian one which defines an image. This makes sense, as when water freezes, it naturally forms a hexagonal lattice, which gives rise to the macroscopic hexagonal geometry we see in snowflakes. The solution to this problem, though, is fortunately pretty simple. By just rotating and scaling a Cartesian grid, we can see it can be made to map directly onto a hexagonal one, with the cell's hexagonal neighbors being the top, bottom, left, right, top, right, and bottom, left cells on the Cartesian grid. So when we want to sample our neighboring cells, we can just sample these 6 cells using a few image translate nodes, and then we can just warp our final texture to visualize the results. We'll be working on the Cartesian grid, but I've built this little diagram just to show how the sim works on a hexagonal grid, just to keep things clear for now. The first step in our simulation is to give each cell a value from 0 to 1, which we'll call the saturation. This corresponds roughly to the amount of free water vapor floating in a given cell, and once a cell's value becomes greater than 1, it becomes ice. We'll call this background value beta, and we'll also set one cell to a value of 1 to serve as the seed crystal for our simulation. The first step in our iterative loop will be to create a receptor mask. That is, for any cell that is ice or has at least one ice neighbor, we'll declare it a receptive cell, and we can compute this in the compositor with this simple setup. For these receptive cells, we'll just add a value gamma to all of them each iteration. For the non-receptive cells, we'll set their receptive neighbors to a value of 0, and its new value is going to be the weighted average of its 6 neighbors and itself to replicate the effects of diffusion. This weighting is also controlled by a variable alpha, where when alpha is 0, the cell remains unchanged. When alpha equals 1, the center value is weighted the same as the average of its 6 neighbors. And when alpha equals 2, the cell's new value is simply the average of its neighbors. This is what that looks like in the compositor, by the way. With that done, we can just add our receptive and non-receptive fields together to get the final state. Running this now, we can see that after only 100 or so iterations, a clear snowflake pattern is emerging. I'll just apply our grid transformation to fix the distortion while we view it, and that's looking much better now. I ended up playing around with this setup for quite a while, seeing how many formations I could get it to produce, and also applied our solver setup multiple times per frame just to speed up the simulation. I usually left alpha at a pretty high value since it has a very dramatic impact on how quickly the simulation evolves. And at least according to the paper we're pulling this from, it doesn't have too much of an impact on the larger scale details of the snowflakes, though it can have massive impacts on the smaller scale structures. Out of curiosity, let's try setting alpha to a value greater than 2, which will negatively weight a cell's own value. We can see this looks more or less normal, but interestingly, there seems to be some kind of threshold around 2.69 where the simulation descends into total chaos. I'm not sure why this is, and the paper that first laid out the model offered no explanation, so if you have any idea why this specific value matters, please leave a comment below. Now, while this model is clearly capable of producing a diverse array of formations, it really falls short when compared to real snowflakes. Dr. Ken Libbrecht is, as best I can tell, the world's foremost researcher when it comes to snowflakes, and comparing the results we can get from this simulation to his real snowflakes makes it clear how limited this model is. To this point, Dr. Libbrecht has published 8 books, and of the 22 snowflakes across all their covers, this model can't authentically replicate even a single one. Obviously, we can't expect to match any real snowflake too well, but it'd be nice if we could get a heck of a lot closer at least. So let's try reworking our model to see if we can get some better results. To start, right now we can only control alpha and gamma while the sim is running, but it would be nice to be able to adjust beta as well. This change is simple enough. I just added a step where each iteration, before adding the fields together, we normalize the non-receptive field so that the largest value becomes equal to 1, then we multiply that field by beta. Now we can dynamically control the amount of ambient water vapor, which is actually something Dr. Libbrecht explicitly mentions doing when he grows real snowflakes in his lab. Next, I feel like just adding gamma to all our receptive sites equally is too simple. In real life, part of the reason snowflakes tend to form clean hexagonal edges and these almost sword-like leaves is because water molecules that hit a smooth edge are far more likely to just deflect off without getting stuck compared to those that hit a coarse or jagged area. This results in gaps getting filled in much faster and the edges being smoothed out. To apply this idea, I just added a condition that we only add the gamma value to receptive sites with greater than 2 ice neighbors. Before I got to my last idea, I really wanted to find a way to get the simulation to produce a kind of thickness map, since a lot of the interesting details we see in snowflakes are completely lost when only viewing the silhouette. My solution here was to create a second thickness field and make it so that each iteration, we take the difference between each cell and the average of its 6 neighbors, and we add that to the thickness value for the cell if it's a receptor. Plus, I added a bit more math so that as a cell's thickness increases, we add a little bit less to it over time. And since our simulation is stored as an image file, we can just store this thickness field in the green channel to keep everything packed together. Running this alongside our main simulation, I'm extremely happy with how this looks. I'm not trying to match any real physics perfectly here, but my logic here was just that smooth or flat regions where the differences between a cell and its neighbors are very small should capture far fewer molecules compared to coarser regions, similar to my logic with our new gamma function. For my last change, I wanted to try letting the receptive cells pull moisture from cells beyond their immediate neighbors. My thinking here was that this would cause dendrites closer to the center, and to each other in general, to effectively starve each other out, and this would allow us to control where the dendrites grow and how frequently they branch off, in addition to controlling maybe even the scale of the simulation. Currently, I'm sampling each cell's neighbors using 6 translate nodes, but trying to expand this to sample several rings around each cell would be way more complexity than I'd like. The more elegant, if slightly costlier solution is to use a convolution kernel. When we convolve an image with a kernel, each pixel becomes the weighted sum of its neighbors, with the kernel providing the weights. For example, convolving an image with a 3x3 kernel, like so, box blurs the image, while this kernel sharpens the image. Since Blender recently added a convolve function to the compositor, all we need to do is create a kernel that falls off linearly with distance while accounting for the distortion in our grid, which looks like this. Now we can just add an exponent variable to our kernel values to control the fall off, I'll add this as a variable kappa, where 2 to the power of kappa is the exponent, so controlling it feels more linear, and I'll repurpose our alpha variable to just be the value of the center pixel from 0 to 1. Our setup now looks like this, and let's give it a go. So this is extremely fun to play with, and if you want to grow your own crystals, the full setup is available for my patrons below, and images of all the node graphs are linked below for free. One thing I did eventually notice is that, unlike with our old setup, this convolution-based method seems to be resulting in slightly asymmetric growth. I'm sure this is just an error on my end though, and it'll be a simple fix once I find the issue. Okay, so it seems that there's an issue with the convolution process itself in Blender. Apparently this function has very slight precision issues, which causes the asymmetry, as all the small artifacts compound over each iteration. I did find that flipping our image on the X and Y axes each iteration tends to minimize the effects of the artifacts, but beyond that, there's really nothing I can do here, unfortunately. Though since this is such a small effect and snowflakes are famously all unique, I think I can, what's the phrase? Let it go? Sorry, that's what passes for humor on this channel. Converting our textures into 3D geometry, by the way, is pretty simple. All we need is a geometry node setup where our texture drives the density of a volume, and then we convert that volume into a mesh. Then we can displace that mesh using our texture again to keep the fine details, and we can also add a smoothing effect to clean up the edges. That's a nice AAA game-ready asset, I'd say. Anyway, that's the video. Thank you all so much for watching, and if you'd like to support my work, I have a Patreon below where folks like these amazing people get access to project files from my videos and unpublished works. Either way though, I hope you enjoyed this and maybe learned something. I've been Logan, and I'll see you all next time.